This is June 15 P41. This is question 9. Okay, now for question 9, they mention this. An isotope of an element is radioactive. Explain what is meant by radioactive decay. So this is actually just you copying the definitions from the notes that I mentioned. It is the spontaneous and random process in which an unstable nucleus disintegrates into a more stable nucleus by emitting alpha particle, beta particles, and gamma ray photons. Okay, this one is worth 3 marks. So what are the specific marks here? You mentioning spontaneous and random is 1 mark. You mentioning your unstable nucleus becomes a more stable nucleus is 1 mark. You mentioning what is emitted, alpha, beta, and gamma is another mark. Those are where your 3 marks come from. All right. And then in part B, they mentioned that in time T, a sample of radioactive isotope contains n number of nuclei. After a short time of delta T, the number of nuclei that has decayed is delta N. State an expression in terms of all those symbols here for number of undecayed nuclei at time T plus delta T. So number of undecayed nuclei that you have left should be your original number minus the number that has decayed. It should be n minus delta n. Okay. And then from there, find out the mean activity of the sample during the time interval delta t. What is the activity? Okay, the keyword here is activity. Activity, as I mentioned to you, is rate of nuclei decay. You find out the number that has decayed, you divide by time. So in your case, it should actually be delta n over delta t. Delta n here has already been stated for you is the nuclei that has decayed, right? Okay. So that one is okay. Then you look at part 3. What is the probability of decay of a nucleus during a time interval delta t? Okay, here they're just asking you for probability of decay first. Your probability of decay is just simply going to be the number that has decayed divided by your original number, delta n over n. But then after that, the subsequent question will ask you, what is actually the decay constant? So decay constant, this one you already know is probability of decay per unit time interval. So you take your probability of decay divided by delta t, it will give you this. Okay, so you get delta n over n times delta t, just like that. So these are all very simple definitions. That is already worth 7 marks. All right. Okay, then you move on to part C. Okay, now in part C, they mentioned this. The variation with time t of the activity A of a sample of radioactive isotope is as shown here. The radioactive isotope decays to form a stable isotope S, and at time t0, there are no nuclei of S in the sample. So on the axis of the figure below, sketch a graph to show the variation with time t of the number n of the nuclei of S in the sample. So let's just try and make sense of what this question is saying. It's basically saying this. You have some unknown element, let's call this element X, is unstable. It decays to become a stable element called S here, a stable isotope S. This one is stable. And it does so by emitting any of these radiation. You can have alpha, you can have beta, you can have gamma, it doesn't matter. Just know that it's emitting radiation here so that you can get a stable element. Okay, so as I mentioned to you before, X will decrease with time, whereas S will increase with time. Okay, so the ones that you're looking at here is actually for that unknown element X. The one that you're looking below is for your stable element S. This one specifically shows you the number of the nuclei S in your sample. Okay, so here you read the question. They say at time 0 there are no nuclei of S in the sample yet. So at T0 no nuclei of sample S. Now from there you need to start drawing the curve. This one you have to make use of the concept of half-life. You see the graph that has been given to you, the first graph that has been given to you is in terms of time, but they gave you in terms of half-life. First half-life, second half-life, as well as third half-life. So let's consider this now. For the first half-life here, you went from here to here. This one is a reduction of 2 boxes. So if you translate it to the graph below, that should mean that after one half-life, it should increase by 2 boxes. Then after that, look at the next half-life. So for the next half-life, you went from here to here. This one has reduced by 1 box. So logically, if you translate it to your next graph, after one half-life, it should by right increase by 1 box. Then you repeat it for the last one. This one, after one half-life, it reduces by minus half a box. So likewise here, after one half-life, it should increase by half a box. Okay, plus 1 box. Sorry, plus half box here. Whereas this one here was plus 1 box. Let me just get rid of this. Sorry. This one here was plus 1 box. Okay. So now you have the complete picture of your graph already. You just join the points together, you will get this. Okay. So that's for this particular question. For page 3 of your worksheet, this one is actually June 2015 P42. Now here they mentioned that the power for a space probe is to be supplied by the energy released when plutonium-236 decays by the emission of alpha particles. The alpha particles, each of energy 5.75 mega eV, are captured and their energy is converted into electrical energy with efficiency of 24%. From here, calculate the energy in joules equals to 5.75 mega eV. Okay, so this is actually just a simple conversion of units of energy, right? So here they want the energy in joules equal to 5.7 mega eV. So we already know before this that 1 eV is actually just 1.6 times 10 power minus 19 joules. And then you have a prefix mega here, you just need to multiply with 10 power 6. So 5.75 mega eV is 5.75 times 10 power 6 times 1.6 times 10 power minus 19. Eventually, your answer will just be 9.2 times 10 power minus 13 joules, just like that. Okay, so that is pretty straightforward here. Okay, now comes the part where they ask you the number of alpha particles per second required to generate 1.9 kilowatts of electrical power. Okay, so if you read back the question, what was mentioned is that you have a space probe that got its energy from plutonium-236 decay. Specifically, when the plutonium-236 decays by emitting alpha particles, the space probe captured the alpha particles and extracted energy out of it. So one way of looking at it could be in a way similar to this. This one could be, say, your source is emitting alpha particles like this. These are your alpha particles. And then your space probe is this thing here. This is your probe. Okay. So what was mentioned to you that the energy of your alpha particle is actually 5.75 mega eV. All right. Your probe is capturing the energy of these alpha particles and then is trying to get an energy of 1.9 kilowatts, or power of 1.9 kilowatts out of it. So here, you're supposed to get 1.9 kilowatts of power. This is your output power. So here, there's a specific input power provided by your alpha particles, but your space probe is converting the power from your alpha particles to your actual output power with an efficiency of 24%. Okay, not all the energy of your alpha particles will be converted to the required energy. Only 24% of it will be converted. So this is one way of looking at it right now. So the question now is just asking you, if you have wanted 1.9 kilowatts of power, how much should your alpha particles per second be? So this one, you can actually relate back to your definition of power from AS, where we tell you efficiency is the ratio of the output to input power. Your efficiency now being 24% changed to fraction is just 0.24. Then output power is 1.9 kilowatts. You're trying to find the input power now. It should be 7.917 kilowatts. Okay, so this is one part. Then from your input power part, the input power is actually your total energy divided by time. So here, for this group of alpha particles that you have, this one here, their total energy is actually supposed to be equals to the number of alpha particles times the energy of one alpha particle. So that's why here it is n times E. Okay, then divide by T because you're talking about power. So here you want to get n over T because this will give you the number of alpha particles per unit time. So you just group n over T out. Eventually you will get n over T as P in over E. So you already know your input power as 7.917 times 10 power 3. And then you already know your energy of alpha particle is 9.2 times 10 power minus 13. So take the ratios and you get the final answer is 8.61 times 10 power 15 per second. These are the required number of alpha particles per second for your case. All right. So this one is pretty straightforward. And then the next part will come to something related to decay constant. So over here, they mentioned that each plutonium-236 nucleus on disintegration will produce for you one particular alpha particle. Plutonium-236 has a half-life of 2.8 years. From here, calculate the decay constant in per second of plutonium-236. So there's an equation that you will have learned that relates decay constant and half-life before this. That one being decay constant is equals to ln 2 over half-life. So here you already know the half-life. You just take ln 2 divided by the value of half-life. You ought to be able to get your value of decay constant. Okay, so because they want it in per second, your time has to be changed to seconds. So here 2.8 years times 365 days times 24 hours in a day times 3,600 seconds in an hour. Eventually you will get the answer 7.85 times 10 power minus 9 per second. Okay, so I'm not sure whether I've mentioned this to you before. When it comes to changing 1 year to number of days, it is strictly speaking multiplied with 365. There have been cases where candidates go and multiply with 360. The moment you multiply with 360, this is actually wrong. Okay, because for some students, they tend to think of it like this. You have 12 months in a year, and then you have 30 days on average in a month. So therefore, the number of days in a year is 12 times 30, giving you 360 days. That's the logic of some students in how they arrive to 360 days. If you have used 360 days, this one will not be correct. The examiner will specifically penalize you for that. So just use 365, okay? So this is okay. Then I move on to the next one. Okay, so if it is okay, we move on to the next one, the next page. Okay, so from here, they mention use your answer in A2 and B1, which is the previous two answers, to determine the mass of plutonium-236 required for the generation of 1.9 kilowatts of electrical power. Okay. So here, just one thing to note, it was already mentioned to you in the previous page. Each plutonium-236 nucleus on disintegration produces one alpha particle. So let's just work with that first. They mention one plutonium-236. Maybe I'll just try it as this. One plutonium-236 produces one alpha particle. Okay. So here, what was mentioned is that in this part, A part 2, your number of alpha particles per second is 8.61 times 10 power 15. Okay, this is the number of alpha particles per second. Okay, now if you know that one plutonium-236 produces one alpha particle, from here you can actually deduce this. The number of plutonium-236 decaying per second is therefore 8.61 times 10 power 15, because you only get one alpha particle when one plutonium-236 decays. If you already know in the first place that the number of alpha particles per second is this value, that would have meant that you have that same amount of plutonium nucleus that was decaying per second. Okay, so here is where you can say that therefore your activity of your plutonium-236 is 8.61 times 10 power 15. Okay, if you recall the definition for activity from last lesson, activity is rate of nuclei decay. How many nuclei have decayed per second? So here, just by looking at this, you can actually deduce that the activity of your plutonium nucleus is actually 8.61 times 10 power 15. Okay, because what you see over here is that the workings will subsequently use this equation. A is equals to lambda n. So the goal here is for you to find out the number of plutonium nuclei, sorry. So you want to use A equals to lambda n. Your activity here is stated to be 8.61 times 10 power 15. This is actually the activity of your plutonium decay. Okay, and your decay constant, you've actually already found it from the previous question, is 7.85 times 10 power minus 9. So here you sub all the values into the equation, you find out what is n. N will be your number of plutonium nuclei corresponding to that particular activity. Okay, so once you have the number of plutonium nuclei, you want to get the mass of your nucleus. Sorry, you want to get the mass of your sample. All right. So in particle physics, it was already mentioned before that if you're interested in finding the mass of a nucleus, you just take the nucleon number multiply with U, because then that one, it was already mentioned to you at that time, U is actually kind of like the average mass of a nucleon. Okay, so nucleon number gives you the number of nucleons inside a nucleus. You multiply with the average mass of a nucleus, sorry, average mass of a nucleon, you will get the mass of the nucleus itself. Okay, so let me just write this properly. Okay, so this is the mass of your nucleus. Now from here, if you want to get the total mass of a sample, you would take the number of nuclei multiply with the mass of a nucleus. Yeah, I better just write this clearer. if you already found out the mass of the nucleus, you take the number of nuclei inside the sample, you multiply them together, you're going to get the total mass. Okay, that's what you're trying to do right over here. Your total mass is the same as number of nuclei multiply with nuclear number multiply with U, because this one by right is your nucleus mass. Okay, this is the mass of your nucleus. Okay, so sub everything in, all the values that you know, eventually you get the final answer is 0.43 kg, which ends up being 430 grams. Okay, so that's for this particular question. Okay, then after that, if no issues with that, I go to the last part of your question. Now, this part here mentions the minimum electrical power required for the space probe is 0.84 kilowatts. Calculate the time in years for which this sample of plutonium-236 in B2 will provide you sufficient power. Okay, so basically what they just mentioned here is this. Originally, you have 1.9 kilowatts of power, but over time, it will decrease up to 0.84 kilowatts. So what they're interested now is how much time would it take for the power to decrease to this much? Okay, now the power will decrease with time according to an exponential curve, because what we know is that your plutonium nucleus decaying is what gave you your alpha particle, and your energy is derived from your alpha particle. So here, if I were to talk to you about the number of plutonium nuclei with respect to time, we already know that it will decay with time, following an exponential decay curve. So if you were to try and relate this with a power versus time curve, your power versus time curve will also be following an exponential decay curve. Because here, the number of nuclei will correlate directly with the power that you get, because one plutonium nucleus is the one that gives you your alpha particle. So it will follow an exponential decay curve. So if it follows an exponential decay curve, there is a general equation that you will have learned from last week. For this one, the number of nuclei with respect to time, this one would just be n equals to n naught exponential negative lambda t. If you want to do the same for power, it will just be P equals to P naught exponential negative lambda t, where P naught is this one. This is your original power, the initial power, and then this one is the final power. So you're interested in finding out the time now. Okay. Now you look at the workings, I actually wrote it slightly differently. I wrote it as activity equals to A naught exponential negative lambda t. You can actually just straight away replace it with this if it makes more sense to you. You can also kind of relate it to activity. Both are the same. Okay. So, but eventually you will come to the same conclusion that power is actually P naught exponential negative lambda t. Just sub in the values you know, you will be able to get the answer. So this one is 0.84. This is 1.9. Don't need to change the power into SI units, because here kilowatts, here kilowatts, the units will cancel off. There's no need to do any kind of conversion. Okay. Then after that, you get exponential negative of your decay constant times t. Your t will be in second, because here it is in per second. So obviously this one will be second. The units will always be consistent with whatever you put in. Okay. So from seconds you change to years, you will eventually get this one, 3.34 years. Okay. So from second to year, you just need to divide by 3,600 seconds, divide by, this one is to get it in hours, then divide by 24 hours to get it in days, then divide by 365 days to get it in years. Okay, so that would be for this particular question. Page 5 is November 2015 P41. Okay, so for this particular question, distinguish for an atom what's the difference between a nucleus and a nucleon? Okay, so if you're talking about an atom, this one is your nucleus, and then you by right have electrons that are orbiting around it. This entire thing is what you call an atom. Okay, so inside your nucleus you have neutrons and protons. Neutrons and protons in this manner. So these are what you call your nucleons. Okay. So if you're talking about what is the nucleus, a nucleus is just the small central core of an atom or small central part of an atom. It consists of nucleons. This statement here is actually not required, but I just write it for the sake of completeness. So next one is, what is actually a nucleon? A nucleon is a particle within a nucleus, which could be either a proton or neutron. Okay, so this one is worth 2 marks. 1 mark here, and then 1 mark here. All right, so this is pretty straightforward. Okay, then from there, they mention that radon gas is a naturally occurring radioactive gas with a half-life of 3.8 days. The activity of radon gas in a room is found to be 97 becquerels in each 1 meter cube of air. So whenever you see mention of becquerel here, this one is already per second, okay? Activity in becquerels is already fixed at per second. So from here, calculate the decay constant in per second of radon. So here, decay constant given, half-life given, automatically you would use lambda is ln 2 over half-life. So ln 2 divided by 3.8 years, sorry, not 3.8 years, divided by 3.8 days change to seconds, you will get 2.11 times 10 power minus 6 per second. Okay, so that would be for number 1. And then after that, the next one will be, what is the number of radon atoms that gives rise to an activity of 97 becquerels? So here, there is mention of number of atoms, and then there's mention of activity. The thing that relates those two is A equals to lambda n. So here, activity is 97, decay constant is 2.1 times 10 power minus 6. Find out what is n. N is 4.6 times 10 power 7. Okay. So your units for both sides is also consistent. You don't really need to do anything about it, because activity in becquerels is already per second. Your decay constant was also already found in per second. So there's nothing you need to do about the units. Just leave it as it is. They will eventually cancel each other off. Okay, so this is okay. Then we move to the next question, next part of your question. Okay, so here you have this. Just let me erase this. Okay, now over here, they tell you you have a volume of 2.5 times 10 power minus 2 meter cube of air in the room that contains 1 mole of molecules. Find out the ratio for 1 meter cube of air, the number of radon atoms to the number of air molecules. Okay. So what you can see from here is basically this. If you are talking about 2.5 times 10 power minus 2 meter cube of air, that one contains 1 mole of air molecules. All right. So what about 1 meter cube of air? How many number of moles do you expect to get? Now for this one, it will probably be best to go and do something like ratio. If you want to find out the number of moles in 1 meter cube of air, the number of moles in 1 meter cube of air, you can actually just kind of do something like ratio here. 1.0 meter cube over 2.5 times 10 power minus 2 times 1. This one will give you the number of moles in 1 meter cube of air. Okay, so eventually you'll get some answer from there. But what you're interested is the number of molecules. You see the bottom part here, number of air molecules. If you want to get the number of air molecules here, your number of air molecules would therefore be number of moles times your Avogadro constant. Because that time it was mentioned to you before that number of moles is number of molecules divided by your Avogadro constant, such that number of molecules is actually number of moles times your Avogadro constant. What you're trying to find is this, okay? Number of air molecules in 1 meter cube of air, okay? The number of radon atoms in 1 meter cube of air, you don't need to do anything because you already found it in the previous question. You see here they told you the activity of radon gas in a room is found to be 97 becquerels for 1 meter cube of air. You subsequently found out what was the number of molecules in 1 meter cube of air. You already found out the value already. There's no need for you to do any calculations there. You just really need to find out the number of air molecules. Okay. So here, that's why you see the working is for 1 meter cube of air, the number of air molecules is 1 divided by 2.5 times 10 power minus 2 times 6.02 times 10 power 23, giving you this amount of air molecules. This one by right is your number of moles. Okay. So once you have the value, just straight away find the ratio. This divided by this will give you 1.91 times 10 power minus 18. This would be the ratio. Okay. After a few examples, you start to notice that the questions are pretty repetitive. Okay. So let's have a look at page 7. Page 7, November 15, P43. There are certain things that we've done before, so we'll probably just go through it very quickly. Okay, what is meant by binding energy of a nucleus is the energy needed to completely separate a nucleus into individual nucleons completely to infinity. We've done this a fair bit of times already, so just recopy from your notes. Now, B data for 2 isotopes of uranium are given in the table below. State what is meant by isotopes. Isotopes is something that you will have learned in AS physics. Isotopes are just different forms of the same element with the same number of protons, but different number of neutrons. Okay. Isotopes is something you learn in AS physics. So you're just reproducing what you learned here. Okay. Then complete figure 9.1. You need to fill in these 2 blanks. So in the first place, it was already mentioned to you before that binding energy per nucleon is just binding energy divided by nucleon number. So if you want to find binding energy per nucleon, you just take binding energy divided by your nucleon number. This one will be your binding energy per nucleon. But if you want to get BE, binding energy itself, you take BE per nucleon times your nucleon number. So in your case, this one is binding energy per nucleon, multiply with nucleon number, you will get your binding energy. Okay. Yeah, another thing that I should probably also mention to you here is please don't round up to 2SF or 3SF for your answers here. If you round it up to 3SF, this one will just be 1780 mega EV, right? Don't write it like that. You just write it as the full SF because you notice the table here is not rounded up to 3SF or 2SF. You see, it's 1802. It's actually all the way up to 4SF. It's the full SF value. So you notice that being put inside your table, your answers should also be written up to the full SF. Okay, don't round it up. Don't round it up to 2, don't round it up to 3. Just use the full SF as it is. Okay, so that is done. Then you move on to part C. Now, part C, uranium-235 has a half-life of 7.1 times 10 power 8 years. Show that the decay constant of uranium-235 is 3.1 times 10 power minus 17 per second. So again, mention of half-life, mention of decay constant. By now, you should realize it's always just going to be lambda equals to ln2 over half-life. So ln2 divided by years, change to seconds, times 365 times 24 times 3600, you will eventually get the answer as 3.1 times 10 power minus 17 per second. Okay, so this is pretty straightforward. And then last one, you have a sample of uranium-235 that has an activity of 5 times 10 power 3 becquerels. Find out the mass of the sample. Okay, so usually when you hear mention of mass of a sample, the thing that usually comes to mind is this: mass total is equals to is equals to your number of nuclei multiplied with your mass of your nucleus. So you need to find out number of nuclei first, but to find number of nuclei, you usually would use A is equals to lambda n, especially when you're given activity. Okay, you see a consistent pattern here. There's certain things that will give it away what equations should you use. Okay, so here you use A is equals to lambda n, activity 5 times 10 power 3, decay constant 3.1 times 10 power minus 17. Eventually, your number of nuclei will be 1.613 times 10 power 20. Then after that, you move on to finding the total mass or mass of the sample is number of nuclei multiplied with nuclear number times U, because this is mass of your nucleus. Okay, so sum everything in, you will eventually get 6.29 times 10 power minus 5 kg, change to grams by multiplying 1,000. You will get 0.0629 grams. This will be your final answer. Okay, so that's that. So you see, the question kind of repeats itself in terms of the workings and the question type. So this is for page 7, if I'm not mistaken. Let me have a look at page 9 first to see whether there's a repetition again. Okay. A and B is actually something you have done before, so we'll just kind of speed through it. So you look at page 9, this is March 2016 P42. Okay, so beryllium-7 is produced in the upper atmosphere and then sinks down onto the Earth's surface. Nuclei of beryllium-7 decay with a half-life of 53.3 days to form a stable nuclei. The activity of a sample of beryllium-7 on the 3 leaf is 39 millibecquerels. Okay, so this one is your prefix milli. It's 10 power minus 3 because it's milli. Okay, so it's milli per second. Then from here, show that the decay constant of beryllium-7 is 1.5 times 10 power minus 7 per second. So same thing, decay constant, half-life given, lambda is ln2 over half-life. Just do your relevant conversion from days to seconds. You will eventually get this answer. Okay, so this one I don't think we need to spend so much time on it. And then after that, for B, determine the mass of beryllium-7 on the leaf. Same thing again, you are determining mass. Usually you will need the nuclear number multiplied with the mass of the nucleus, but you need to find out the number of nuclear. To find the mass, you need the number of nuclei times with the mass of the nucleus. In the first place, you need to find the number of nuclei. And so to do that, when you're given activity, you will need to use A is equals to lambda n. Okay, so sum in the values. Activity being 39 millibecquerels, you need to make sure that the 10 power minus 3 is inside. This one will then be per second. And then you divide by a decay constant, which is also per second. You will have no issues from that. Eventually, your answer becomes 2.582 times 10 power 5. Sub it in and find your mass of your beryllium. Okay, so this is pretty straightforward. Okay, then for part C. Part C is using your decay equations. Decay equations, A equals to A naught exponential negative lambda T. So the leaf is covered so that no further beryllium-7 is added to the existing sample from the atmosphere. Calculate the time that must elapse before activity of the sample is reduced to 2 millibecquerels. So this one is just you trying to find out if you had 39 millibecquerels in the first place, you want it to reduce to 2 millibecquerels, how much time would have actually elapsed here? So you know that in terms of activity with respect to time, it will usually be something like this, okay? So you're going to use this equation. A equals to A naught exponential negative lambda T. 2 millibecquerels equals to 39 millibecquerels times exponential negative 10 power minus 7, 1.5 times 10 power minus 7 T. Ln both sides. You eventually get the answer is 1.98 times 10 power 7 seconds. Okay. So same thing as before lah. Just notice that the units don't need to be changed in any way because this one is millibecquerel. This is also millibecquerel, they cancel off. And then because this one is in per second, this one will be second. All right. So this is your final answer, 1.9 times 10 power 7. That one is pretty straightforward. Okay, next one will be page 10. This one is June 2016 P41. Okay, from here, they mentioned copper-66 is a radioactive isotope. When the nucleus of copper-66 decays, the emissions include a beta minus particle and a gamma ray photon. The count rate produced from a sample of isotope copper-66 is measured using a detector encounter as illustrated in the figure below. State 3 reasons why the activity of your sample copper-66 would not be equal to the measured count rate. So they're just basically asking you, why is it that the count rate R is never equal to your activity? So this one we actually went through it in detail in the last lesson of your, specifically inside your notes, page 8. I went through with you the points why your count rate would not be equal to your activity. So these are actually the points. You can choose any one of those points. They are reproduced inside your work solutions here. So the most common answer will obviously be the fact that when your radioactive sample is decaying, it tends to emit radiation in all directions following a sphere. It's emitted out in a sphere like this, where you get your alpha, beta, and gamma radiation. So let me just write it out. You will get your alpha, beta, and gamma radiation. So, but the problem is that your detector, which is this one, will really only detect in this direction. Okay, so whatever got emitted in the other directions like this will never ever be detected. That is one of the reasons why your count rate will never be the same as your activity in the first place. So your answer here would be radiation is emitted in all directions, but the detector only covers one direction. Okay. And then the next one that you can probably say also is the fact that your sample may not be the only radioactive source here. There could be other radioactive sources around you in the form of background radiation. So you could also have background radiation, which is contributed by other radioactive sources. So you can say here, background radiation is included inside your count rate. So it actually adds to your count rate. Okay, the statements in blue is more like just explanation. You're not really required to explain because your question here just says state. They didn't say state and explain. Okay, so just state what are the reasons. Don't need to explain so much. And then after that, the third reason is radiation is absorbed by both the air and detector window before reaching your detector itself. So your detector is here, but before you're able to go to the detector itself, you had to pass through a layer of air, and you also have to pass through your detector window right over here. So before it's able to reach the detector, it has to pass through the air and window. So it could be that the radiation itself is really absorbed by both of them. Okay, so that's one. And after that, the other ones would be the ones written in red here. So the one that in red that most probably is understood well is this. If you have an element X which is unstable, it could decay into element Y, which is also unstable. But in the process of it decaying from element X to element Y, it already emits radiation, alpha, beta, and gamma. This is what you're supposed to detect. Okay, but when your element decays from X to Y and Y itself is also unstable, it will also emit its own radiation of alpha, beta, and gamma. So your detector is also detecting this. This would account for why your count rate is different from your activity, because your daughter product is unstable. Let me just write this. Because your daughter product is unstable and also emits radiation, you're also detecting that. Okay, so that's for this one. So your element Y is also unstable. You eventually decay until it becomes stable. Let's just call this element Z. Okay, so this one is for this. Now, some other reasons could be self-absorption of radiation in the sample, where we tell you that your radiation is actually just absorbed back by your sample. It got emitted, but then it went back in. Okay, that's what self-absorption of radiation means. And multiple possible counts from each decay, that one is actually related to this. You have daughter product being unstable and also emit additional radiation. Okay, so these are some of the answers. It will be probably good to just remember at least 4 of them. Okay, this is something just that you need to remember. Okay, so if that's okay, then you look at part B. Now in part B, they mentioned that in a time of 42 minutes, the count rate from the sample of copper 66 is found to decrease from 3.62 times 10 power 4 becquerels to 1.21 times 10 power 2 becquerels. Find out your half-life of copper 66. So this is talking to you about exponential decay again, specifically that of count rate. You would use the equation R equals to R naught exponential negative lambda t. So your final value is 1.21 times 10 power 2. Your initial value is 3.62 times 10 power 4, multiplied with exponential negative lambda 42. Okay, now here, your time is 42 minutes. Okay, this time here you get is 42 minutes. So the decay constant that you get, the units ought to be consistent. So this one will actually be per minute. Okay, so your decay constant here is 0.1357 per minute. Okay, I forgot to add in the power negative one there. Okay, so your decay constant is this one, but then after that they want you to find your half-life, right? So knowing the decay constant and you want to find the half-life, you need to use this equation. Lambda is ln 2 over t half-life, so you get 0.1357 equals to ln 2 over t half-life. Eventually, it will be 5.11 minutes. Again, same thing here. You can see there's some consistency in the units. If this one is per minute, this one would be minute. Okay, so you're getting the answer straight away in minutes at 5.11. Now, C is related to what you learn in quantum physics, specifically your emission and absorption spectrum. Okay, so here they mentioned the gamma ray photons emitted from radioactive nuclei has specific energies dependent on the nucleus that emits the photons. By comparison with your emission line spectra, Suggest what can be deduced about energy levels in nuclei. There are discrete energy levels in nuclei. So if you revisit a little what you learned in quantum physics, your emission line spectra, which was basically a series of colored lines on a dark background. Sorry, let me just rewrite this. Emission line spectra in quantum physics is just referring to a series of colored lines on a dark background where you have, say, different colored lines, green, yellow, blue, red, pink, whatever. So these colored lines here represents to you a specific wavelength and a specific energy of photons. So the conclusion that you got from there was that electrons have specific energy levels, or rather than saying specific, sometimes we call it discrete energy levels. So here the question says, by comparison with your emission line spectra, suggest what can be deduced by the energy levels inside your nuclei. So here they told you gamma ray photons emitted from your nuclei have specific energies depending on the nucleus emitting the photons. If you compare with emission line spectra, what can you deduce from that? Your conclusion should be similar to that of the one in quantum physics, where you say that there's specific energy levels here. But rather than saying that for electrons, you say it's for your nuclei now. Okay, there are discrete energy levels inside your nuclei. Okay, because your photons here are not emitted from electrons. Jumping energy level is actually emitted by your nuclei itself. Okay, so this is just one mark. It's actually related to quantum physics. Then if you're okay with that, we move on to 12, I think, page 12.